Hey chemistry, we are here today to learn about nuclear chemistry and nuclear reactions, which are vastly different than all other reactions that we've talked about before. So in other reactions, we've talked mainly about what the electrons do, because electrons are what holds elements together, what forms those ionic, covalent, and metallic bonds. But in nuclear reaction, something completely different happens. So first we just want to have a little reminder. What are the three main components in an atom? At this point we should know protons, neutrons, and electrons. That should roll off your tongue like the ABCs. Electrons are negative, protons are positive, and neutrons are neutral, which means they have no charge. And they are there really just to hold all those positive charges together, because if you recall, like charges want to repel or get away from each other. So if I put a bunch of positives together, they don't want to stay there naturally. Neutrons are there to hold them and help keep them in place. The atomic number is going to start to become very important when we talk about nuclear reactions, and that represents the number of protons an element has. It's the elemental's identity. So if you change that number, you're going to be changing the element completely. The atomic mass is also going to start to become very important, because remember, mass is conserved, so whatever we start with is what we end with. And that will be the number of protons and neutrons in the element's nucleus. So you add those two together, that'll give you the atomic mass. The structure or the identity of the element, like we were talking about, is determined by the protons. And in the past, like I said, we were talking about electrons and what happens to the electrons. Either they're being given or taken, you're losing or gaining in the case of redox reactions. Acids and bases are all about what those electrons are doing in that Lewis definition, if you recall. But in nuclear reactions, we are going to be talking about the nucleus, which does not have electrons. It's only protons and neutrons. One of the big things that we hear all the time in our everyday lives is that radioactivity and radioactive nuclei. These can be both helpful and harmful. We use radioactive nuclei a lot in biology to conduct different research things. So for instance, you can tag proteins that actually fluoresce, so they're slightly radioactive, and under a black light will fluoresce, and then you can follow where those proteins go. It's something I did when I was in college. I was able to look at green fluorescent protein in mosquitoes, and we followed what happened in the hemocytes or blood cells of mosquitoes. Super interesting, but most of you probably don't care. So you also use radioactive nuclei in medical treatments and medical tests. Molybdenum is a big one that's kind of coming up with different medical tests to determine like the presence of cancers in certain organs that you don't normally get to be able to see them on a scan. So like for instance, x-rays are only used to see bones. It goes through all your soft tissues, but it'll stop at bones. So you can't use an x-ray to diagnose cancer, but you can use radioactive things like barium will fluoresce, and then they can see where it goes in your body and see if things like in your gastrointestinal tract are behaving the way that they should. And we also use radioactivity as a source of energy in our society. So we aren't building new nuclear power plants. That's not something we've done pretty much since the Cold War. However, we are maintaining all the ones that were built in like the 60s and 70s. We've got the one in Point Beach. There used to be one in Kewaunee, but they shut that one down. There's a couple in Iowa. I think there's like a Duane Arnold in Iowa. Florida's got a bunch. So nuclear power plants need to be by water, which is why you don't really see many of them in the center of the country. But because we've got a huge lake, we are able to have nuclear power plants, like Michigan, obviously. And so all the power plants, nuclear power plants, would be built along Lake Michigan or along another water source. All right. Radioactivity is all about energy associated with the nucleus. So the energy involved in these processes are millions of times larger than those associated with our normal chemical reactions, right? So in a normal chemical reaction, think of like a hot, one of those hot things that you break and you put in your gloves when you're ice fishing because it's freezing. Blanking on what they're called. That's okay. I'm sure you know what I'm talking about. That is a normal exothermic reaction. It releases energy in the form of heat, and it'll help to heat up your hands. Now, they can get very hot, but not enough that they're actually going to burn you. However, in a nuclear type reaction, that will often cause severe damage and death depending on your level of exposure. I recommend, if you have HBO, to watch the Chernobyl series. It's really interesting. There's some minor scientific inaccuracies, but for the large part they got it right, and it's really fascinating to see the damage, the cellular damage that nuclear reactions can cause in a short span of time. So when we talk about nuclear reactions, we also have to think of the word isotopes. You've heard this one before, but as a reminder, isotopes are a chemical that has the same identity, so the same number of protons, but a different mass. What would cause that difference in mass would be the number of neutrons. So if I'm talking about the same element, it has to have the same number of protons. For example, we can have carbon-12 or we can have carbon-14. Both of them are different forms of carbon, so they have to have 6 protons. But one of them will have 6 neutrons to get the 12, or 8 neutrons to get the 14. So just a difference in the number of neutrons. Remember, when we're looking at our periodic table, X here is just representing any element. A would be the mass number, so the protons plus neutrons, and Z down here would be the atomic number, or just the protons. So again, carbon, which is our element symbol, 14 for the atomic mass, and 6 for the atomic number. When things decay, when nuclei decay, I should say, it can happen spontaneously or it can happen in a controlled way. So many nuclei are just naturally radioactive. They will naturally decompose, again, because positives don't like to be next to each other. So it's just a natural process that occurs all around us all the time. We've got carbon-12, carbon-14 all around us. It just happens, and they decay. They will form different nuclei or plus one or more particles depending on the type of decay and what they decay into. This is what we would call a nuclear equation or a nuclear reaction. The atomic number and mass are always going to be conserved because for the large part in our everyday life, mass and matter are conserved. So that means that what I start with, the sum of what I start with, has to be the sum of what I end with. I'm not going to lose mass. I'm not going to lose protons and neutrons along the way. They're going to be accounted for. These are the different types of radioactive decay that we're going to be covering in the next lecture. So there's a few different types: alpha, beta, gamma, positron, and electron capture. Alpha and beta are going to be where we spend most of our time, but we'll be covering this next.